coming. Right after the lunch is usually the hardest hour. That should really be reserved for a nap time if you think about it. So I'd like to start this presentation with a bit of a teaser to give you a sense what we're going to be talking about in the next 20 minutes. So I'll talk a little bit about insurance risk analytics. So imagine you have an insurance company with 5 million clients that have a home insurance policy with this company, and the data that's underlying that is like a record set with 5 million records in it. Now you have a model, a hurricane model, that really consists of 50,000 stochastic events. So these are hurricane events, simulated events that may occur and may affect those homeowners. Now the type of calculations you'll have to do for each one of those 5 million policies and each one of the 50,000 events, we need to evaluate the policy. And that includes typically basic financial terms like deductibles. You might know that from your own homeowners insurance and limits. But there's also more complex financial terms that have to be evaluated. And then we are a reinsurance company, so we actually have multiple hundreds of clients that are insurance companies. So if you think about that join that we did here, the 5 million and the 50,000, you can multiply another 100 on top of that to give you a sense of the kind of data that are produced by the models that we use in order to evaluate the risk. So my colleague Shuai will talk a little bit later. He's a developer, so he has the interesting task to actually build and maintain a production level system based on Spark. And I'm the scientist, the data scientist. Among others, I'm always interested in seeing kind of the raw output of these models. So I like to see the full set, whereas the production systems usually already knows the metrics that it needs to distill, and those are aggregate metrics that are predefined and can be calculated. So those are the two sides of the analytics. So this is how we plan to do this. I'm going to tell you a little bit about reinsurance, take a few minutes of your time to get you up to speed on that, because that really motivates how catastrophe models are built. And then I'll give the stage to Shuai here, and he'll take you on the journey that we've gone through from MapReduce to Spark, and then I'll be back here for conclusions. All right, so what is reinsurance? Reinsurance companies actually provide insurance to insurance companies, and the type of risk that they typically cover is due to natural catastrophes such as hurricanes and earthquakes, some cases also man-made like terrorism. So you might think, well, if insurance companies need insurance, who's going to insure the reinsurance companies? And that's an obvious thought. And it might seem a little bit like we're in a vicious cycle here somewhere. The reality is there is such a thing as reinsurance for reinsurance companies. It's called retroinsurance. And if that worries you even more, that infinite cycle, I can tell you if something like a bad hurricane happens in Florida, the way this actually really pans out is that the loss of that catastrophic event really gets shared globally between all of the reinsurance companies in the world, so that none of the individual companies will actually have to go bankrupt over the big losses that you can get from something like that. I want to go into a little bit more detail to give you a little bit of sense. So here's an example of an insurance company that covers this portfolio of houses here. And really, an average year would look like this. So you have 3 damaged houses. 2 of them have small damage. 1 of them might have burned down. And this is good for the insurance company because they collect a premium up front, and they can set aside enough to actually cover this type of average year. So everything is within the budget. But now, what happens if a hurricane hits is all of a sudden many properties are going to be damaged at once in that year, and the loss is actually going to be much more than average. So from a statistical standpoint, I'm already talking about a distribution here because there's an average to this annual loss, and this hurricane event is really in the tail of that distribution. And the reason I'm saying that is for us in the reinsurance, it's really important that we understand the entire statistical distribution and the uncertainty that's given there. And the other thing here is the reason why this loss is so high is because losses happen at once for many locations, and implicitly that means locations are correlated. So our business is really to understand uncertainty and correlation, and the catastrophe models that have evolved to help support that have evolved in that way because of those priorities. So what can that insurance company do to prepare for such a severe event? Well, they will end up actually writing a contract with a reinsurance company like ours, and the type of agreement that you would get, for instance, is we'll agree that we will cover, for a premium obviously, we will cover up to 12 million loss as soon as they have to pay more than 10 million. It's called an excess treaty, and their average could be around 10 million, so they're writing this treaty that for the event that they actually have to pay out more than average. And as I sort of hinted at before, it won't be just one reinsurance company participating in that contract, but usually one company will take 5%, another company 10%, 20%, so that loss kind of gets diversified across the entire reinsurance industry. And that's the mechanism that sort of really provides this insurance for uncertain events. Yeah, so this is also kind of the reason why catastrophe models have, or we call them CAT models, have evolved the way they have. And I want to give you a sense what the components of a CAT model are. So on the one side, we have the exposure data. So that's really data that we receive from our clients. And they give us, so the size of that data could be, depending on the size of the company, between 1 and 5 megabytes, 500, excuse me. And they'll give us information about the buildings of the policy that they cover. And then things like the occupancy type. Is it residential or commercial? Construction type, is it wood or masonry? And the age. And there's more attributes that can be captured, more detailed information. And the more information we have, the better the models can predict. And on top of that, we get the policy information. Again, I hinted at that, deductibles, limits. But in many cases, also quite more complex terms that have to be evaluated. So that's what we get from our clients. On the other hand, there's the model data, and that's the bigger one. It's kind of more the static data. The client will change from one client to the next. The model data is the static data that we have, and that can, depending on what it is, a hurricane, quake, and the region that is covered, can actually already reach into the big data sizes. And why is it so big? Well, in the example of a hurricane, it would be common to have like 50,000 stochastic events. And for each one of them, typically we pre-compute the footprint of the event. So imagine a hurricane landfalling in Florida. Then in the vicinity of Florida, all of the lat longs that are affected there are pre-computed. So we know what the maximum wind speed given during the storm will be there. And this data is then used to actually evaluate the damage of each one of the houses that is in the exposure set. And for that last step, we use so-called vulnerability curves. They just help us translate wind speed into damage of the property. So what kind of analytics do we do? I want to sort of tell you about that a little bit more. So apart from evaluating deductibles and limits and those financial terms, we also, since we're the reinsurance and write reinsurance contracts, we also have to be able to evaluate those contracts. And then typically a system that we would have, a production system, will calculate standard risk metrics. So for instance, what is the cost of this contract? So what is the expected loss that you will get from this contract? But equally importantly, as I mentioned that before, we also want to have probabilistic metrics. So we might be interested in knowing what's the probability of exceeding more than 2 million, because we ourselves also have to protect ourselves against those tail losses. On the other hand, then you have the data scientists and scientists in the team that also want to get additional insights from the models and not just those standard business metrics. So they would like to do interactive analytics or custom analytics on intermediate data sets. So another way of putting what the CAT model does is this kind of blue sky version. So if we didn't have to worry about cost, performance, runtime, and all that, and we had a client data set, this is what we would do. We have our hazard data, so the hurricanes 1 through 3, all the way up to 50,000, and then the exposure data set, which might be millions of records. In my example, I have one policy that covers one building, another policy that covers 3 buildings. And every policy, or every building, in fact, will get evaluated for every hurricane. So you really have a cross product here. I did say sparse because not every building is going to be in every event footprint. So sometimes a particular building doesn't get hit there. So that reduces sizes. But it's still not an uncommon thing to see a few terabytes of data if this data was ever materialized. And I want to say a little bit more about that. Again, if you're trying to build a production system, it might not be necessary to materialize that data at any point in time because you can calculate summary level statistics along the way, so it doesn't really ever come to, materialize. But on the other hand, when we do want to sort of investigate or explore the data and find new methods of actually looking at it, then it's best to actually have it materialize, and we do this for smaller subsets and then run our analytics against those. So I want to say traditionally how CAT models, catastrophe models, have evolved is along one of those dimensions of this cross product, you have a very natural parallelism. People often call it embarrassingly parallel, and it's true. You could really, this is how CAT models used to be built. You can really evaluate one hurricane at a time, run it across all of the exposures, and then maybe even aggregate the data up, and then you have to solve 2 problems. You can do all of those things in parallel, and you don't have the big data, big intermediary data that you would have. But the obvious problem with this kind of things, as soon as somebody asks a question that's sort of not at that aggregate levels, for instance, I could ask, for policy 1, what were the top 100 events that hit that policy? All of a sudden, the data sits on different cores, so you have to actually aggregate data across cores, which is not embarrassingly parallel anymore. And that's the reason why you have to start thinking about systems like Hadoop or Spark in the first place. Okay, with that, I would like to ask Shuai to come to the stage and talk a little bit about MapReduce and Spark.
Good afternoon, everyone. My name is Shuai. I'm a senior software engineer from Validus. In the past few years, I work closely with research team to write up what we described here into a day-to-day used production system. The application was start with the MapReduce, and then it was quite successful inside the company. And then later on, 2 years ago, we turned the system to the Spark platform. Here, I won't, because of the time limitation, I won't discuss a lot about underlying architecture because, be frankly say, this is a very Spark application. We don't use a lot of cool things here talking about like the Spark streaming or something like Kafka or other big data components. We are purely Spark itself. So we'll focus on to discuss the reason why we want to migrate from the MapReduce to Spark, and also what we can benefit from it. So here it is where let's review the requirement, which is from the original service agreement between the IT and the research team. Basically, just as Georg just now introduced, from the CAT model size at the beginning where I received, it is about 100 gigabytes to 4 terabytes. And the data from each exposure set, it is up to 500 megabytes. So intermediate results are based on our prototype analysis is from 10 gigabytes to up to 100 terabytes. Daily analysis, we will start from up to 100 daily, and then we are expecting it will grow until when the scope of the project enhanced, and also new model comes in. In our business, because of reinsurance industry, we need to sometimes, for the kind of year end, we have burst requests to analyze the whole year's analysis or do a massive analysis there. So it will be kind of like, we need to run up to 2,000 analyses within few days time. So generally speaking, the analysis the research team wants, it is like any analysis can be finished in less than 30 minutes. As a comparison, our internal third-party vendor system doing a similar analysis, they will take from 30 minutes to 10 hours, or sometimes our internal CAD modeler told me it will take few days to finish some big analysis. Cost, on average, we want each analysis will be less than $5. This is kind of important. And we also need to support very complex algorithm. As in my career, I involve a lot of projects named as analytic, but this project is very different. This is not really analytics tools. Basically, we are pricing tools. You can imagine, basically this product, it is answering a simple question. When a reinsurance company comes to you to try to insure 5 million policy, how much you want to charge them? That's the first question we want to answer. So this it is. And you can imagine, like, other than the first step of the application, it is try to run a simulation throughout for every event we want to simulate for individual properties inside the exposure. Then we carry the loss throughout the whole policy terms from the deductible limit. The challenge here it is like global-wise, the insurance policy in the primary insurance and the reinsurance, they are very complex. It is very different for country by country and for the different risk type. So we need to cover all these things, and including a lot of customized business logic between the insurance and the reinsurance industry. The application, it is start with MapReduce. And then here is some overview we achieve at the beginning with the MapReduce. Our application is built on the cloud, AWS. It is a hybrid system, which means like we only use EMR to run the analysis itself. Our workflow, it is still in-house. And the cost per analysis basis from $0.50 to $15. On average wise, we don't have the exact numbers, but it is kind of like $2–3 per analysis. The reason it is like when we start a cluster, you need to maintain the infrastructure it's running. You cannot say there's no analysis, I just shut down the infrastructure. And then the time per analysis we achieve, it is from 5 to 30 minutes. And based on the standard cluster we use, it is the 5 R3AX large nodes. Then the issues. When we have this, although we already achieve what the request from the business user, we mean a service agreement. But we found out it is because of the success of the project, it sounds like more and more expensive because like it is popular. Then people tend to like run more analysis. They just change some factor and then just run it again and again because it is sitting on the cloud. It is so easy. There's no say if you have an in-house system, it is very popular. And then a lot of people submit a request, they drop a paper, they just lay up there. But on the cloud, we just can open more and more custom there. So it is like this convenience to actually give the incentive on the user, it is like run more analysis there. And then the cost that we can expect, it is grows dramatically. And then later on, we see the resources cap and the limitation on the EMR Hadoop. Today, the AWS EMR Hadoop has a limitation on the 6 gigabytes memory per mapper or reducer slot. So which means when you write a MapReduce program, each mapper, you cannot access more than 16 gigabytes there. You can imagine our application doing a simulation, we need to maintain a very big, certain kind of big preload part of the model, and also we need to build our the whole exposure simulation inside the memory. The size, it actually depends on different kind of risk group and exposure size, but certain kind of it is very memory intensive one. And then fragmented workflow. In my experience, I'm a developer. To deal with the MapReduce on the Hadoop, it is like not something very nice experience, because like it is basically I can say we have a Spark application. It is very difficult you say you have a Hadoop MapReduce application. The reason it is like you better say you have an application around MapReduce, because MapReduce itself, it is a batch independent batch job. It is like you need to prepare the input format for the MapReduce, and then later on you need to write another process to process the output. It is the workflow. To me, it is I have a lot of unnecessary data preparation there, and consider in a big data, it is a kind of also a cost. Something it is very important, it is the MapReduce, it is very inefficient on the caching and sharing the resource. I will discuss more on in the next slide. And the inconsistent on or off cluster mode. Just now, we're always talking about 5 million, 10 million locations, and sometimes if we have a company-wise exposure, you will go to like 20 or 30 million exposures. But of course, we are our company later on doing some, have a sub-company, which is doing the primary insurance. They have much smaller requirement, let's say 1 or 2 locations. You don't want to, pay $5 to give every code on, someone come to you to code a flood insurance on his own home house, right? So we have built another off-cloud or say off-cluster running system, which is provide real-time things. This, it is like, actually we wrap up off-cloud MapReduce simulator to run the MapReduce code without Hadoop. This, it is a trade-off, but it is not something very good design for us, because like, we cannot reuse our current code, and they have a lot of redundancy and they create a different branch on the development. And then why Spark? To me, at the moment, the most important thing to me, it is like Spark allows us to share the memory and cache for all executors on the same instance. When the first time I see Spark, people told me, it is a lot of people talking about like Spark need a lot of memory, right? But actually later on I realized on the Spark, it even uses less memory in my application. The Spark actually demands much less memory comparing to MapReduce. The reason is here. The MapReduce, it is a multi-processing system, and then the Spark is multi-threading. The multi-processing system means like each process itself, they have its own isolate memory area. So if say, for me, if I want to run some model, I have a lot of to improve the performance, I have a lot of preload cache. Say it is maybe, I just give an example like in an earthquake, like US earthquake, it may take like 2 or 3 gigabytes preload some model data. So in this way, in a MapReduce way, each processor, its memory has 1 copy. You can see the calculation here. The Archie AIX instance on the AWS actually provides 244 gigabytes memory, which is equal to, by default setting, it is 32 instances you can run in, and then so each one have around 7.6 gigabytes memory. Actually, in a real practice, you can't have so much. It is around, I can't remember, by default you will have like 6 gigabytes around that. So it means like, if you don't change any design, any configuration, each mapper can use 7.6 gigabytes. If you have 4 gig preload cache, then it eat up more than half of the memory you can use. And then in the Spark, it's totally different story, because Spark only need to keep 1 copy. Instead of like in the MapReduce, you need to keep 32 copies. You save like more than 100 gigabytes overall on the instance. So this actually means when you try to run something apple to apple, it is much less memory required on the hardware, which actually means much less cost. We know in the AWS, they have like same computing power. They have a memory optimized instance called R3AX, which is also 32 core, which comes with 244 gig memory. Currently costs $2.6 on spot price. And then compare much more, slightly faster CPU and much less memory. One is called C3AX, large instance only cost $1.8. So in this one, even this, you already save like more than 30%. But this is not the most important part. After the conversion, we know based on the same analysis, exactly the same analysis, Spark version give us like 30 to 50% faster. But be frankly say, 30 to 50% faster speed is unnecessary for us to do this migration. The more important thing it is that because we have much less memory requirement, which means this allows us to carry multiple analyses in the same Spark run. This means like we have like 10 to 30 times bigger throughput with the same cost. Give you an example, it is you can imagine it's similar as like when I introduce internally, it is like when you have a trunk, you can carry some load, right? And the Spark is in our system is run as a kind of a train. You are not run analysis by analysis. You are trying to run 10, 50, or maybe like up to 100 exposure at the same time. This one actually, because like we benefit from the shared memory, this means like we open the door for us to catch much more things in the memory and communicate between the multiple threads. And then hardware means also come with much less memory requirement. Overall, we see the whole system after conversion is saved 90% of cost. If you say, talking about like if you have a burst request, even like you will save more. But usually we will say this gives us a much bigger bandwidth to take in a new analysis coming. As a developer, I always focus on the design or the something like implementation details. With the Spark itself, the implementation, it gives us a much better code quality. It is kind of give us like, I don't have an exact number here, but it's kind of 30 to 50% less code comparing to MapReduce implementation, because at the same time we save a lot of unnecessary steps. It is a consistent code base for the on and off cloud execution. Our internal, because like actually, personally, I really love the idea about running the Spark without cluster to do the testing and the development. And the unit test is much easier to integrate and to implement and integrate with to do the integration test. And also, it is much easier to implement multi-step complex business workflow. Just now as what I described, with the Hadoop MapReduce, it is very difficult. You say you're running a MapReduce application. You run a batch and get a results. It is a kind of a reporting tools. But you try to build a complex business logic, Spark is much, much easier. And then it also offers much more options when we design when we do an architecture design. You can see it is like it is easier to integrate with our in-house other homegrown applications. It is much more flexible on the input format and also output format, because like in MapReduce, you very likely you only have one format, and then you have other things to processing. And in the Spark, you can for each stage you can output the things you want, and then you also allow some very complex optimization algorithm possible. Like we can do the distribute standard deviation calculation, a lot of like customized optimization is possible in this way. Okay.
Just to wrap up and throw the most important points back at you again, I think catastrophe models are probably a little bit different than some other big data projects in that we don't necessarily start with big data, although you could argue that, but they really create big data along the way because of that big join that I described earlier. They require complex custom analytics like evaluating functional terms that are not usually present in other Spark projects, I'd say. And our conclusion is really that Spark is well suited to address the challenges of businesses that run CAD models at on a large scale. And with that, we'd like to thank you for your attention and open things up for questions.
I'm wondering how you calculate the costs per analysis. When you run the analysis, how are you calculating the costs in dollar values, like $5 per analysis or so?
Oh, okay. So because like we are running on the AWS, it is pretty easy because like on the EMR we have pre-set up the cluster the cluster configuration. When the cluster up running, we know the cost, and then definitely it won't be exactly accurate because never can have a lot of factors to affect it. So when we calculate the cost, we based on the real time, for example, on the daily, because in our business model, we only run 8 hours per day. We every day in the morning, first analysis coming, the in-house application will automatically start up the cluster on the cloud. And then based on the further workload, we maybe will expand it or start more clusters. And then the day end, we will shut it down. We also involve a lot of get benefit from the spot price and the reserve price, all this kind of benefit. But overall, we have a picture how much analysis, how many analysis we're running, and then how much we pay every month's bill on the EC2. Yeah.
Right. I don't see any other questions. Then thank you again for your attention and enjoy the rest of the conference.